It was an expression for the voltage and current relation for an inductor. Okay. Again, if we transform this, then the equation will be okay. SF. If I rearrange it, right? Huh? Is it capturable?
Yes, sir.
Okay. So this time, let's suppose I think it is a voltage equation. Okay. This term is a voltage term. Current multiplied by. Okay. So if this is the impedance, V is equal to I is equal. Okay. This term should be the voltage term. Voltage, voltage, voltage. Okay. This is the magnitude of initial value. Okay. I will come to it after completing this session. Okay. On the initial values. Okay. So if I have to model it in the circuits, then the situation is this is the voltage across these two. So inductor with impedance SR and current flowing. Okay. And a voltage source with the magnitude VFS.
Yes, sir.
Yes. Voltage across this inductor, current flowing through, and the impedance.
Yes.
Okay. Then minus sign. Okay.
Because and clockwise.
Okay. We don't have any option to put the voltage source in this configuration. Minus polarity, negative polarity is upward, connected with the inductor. Okay. The positive is here. Magnitude of this. So if we have an inductor, in the time domain, and we have to transform the same inductor in the Laplace domain, then one of the possibilities is this configuration. Okay? Not only the inductor having the magnitude SL, which was previously in the frequency domain j omega s. Okay? I'm comparing with that as well. Okay? An inductor in the time domain was transformed in the frequency domain, in the phasor domain was j omega. Okay? But in the Laplace domain, there will be a source as well. Okay? That's it. Okay? The other way of that was the voltage equation. If we form a current equation divided by SL.
Yes.
Okay? And rearrange. So we will have, where is the equation? SL plus S. Okay, sir?
Yes.
And if we have to model that, current across these current. So just the methodology that we had adopted for the case of capacitor, on the same lines, we could see that this is the if you have an inductor in the time domain, then other possibility to transform according to situation, according to demand of the circuit. This not only the inductor having the impedance Sn, but a current source in parallel in this direction.
Yes.
Okay. So let me redraw the capacitor equation. 1/Sc and 1/Sc current source. Okay. So if you have a capacitor in time domain, you could transform like this. Okay. If you have an inductor, then you can transform. Okay. In your book, in your examples, they have used certain sets. Okay. For example, for the case of inductor, they are using this one, as the inductor stores the current, and for the capacitor they are using this one, as the capacitor stores the voltage. This is one of the reasons that I could understand that why in the examples he is using these combinations. Okay, there might be a shortage of time or opportunity that he did not use the other things, but when I use the other alternatives, the answer was same. Okay, for example, contradiction to the book's notation. If you use other set, then the answer will be same. Okay, so one could use depending upon the situation. Okay, the last thing before going to solve the examples, we claimed that Laplace entertains the initial and final values. Okay, we claim that Laplace has the capability, has the ability to provide us with the complete solution. Okay, which will entertain the initial values. So here is the evidence. Okay, in the frequency domain, in the phase, when we were using the phases and transforming them in the frequency domain, we only had the steady state solution. We don't have these initial states. Current at 0 or voltage at 0. Okay, just before the 0, in order to cover the initial step. Okay, the time at 0. Okay, for example, now let's suppose if initial conditions are 0, if they say that the current flowing in the circuit or the current flowing through the inductor at I is equal to 0, at time t is equal to 0, I of 0 is equal to 0, or V of 0 is equal to 0. Ibrahim, do you have something to share? Okay, sure? Okay, then our this configuration will be simplified. How? Voltage source, 0 magnitude, 0 multiplied by 0, 0. Okay. What was the meaning of 0? A voltage source is providing 0 voltage.
Short circuit.
Very good. Okay. A current source providing 0 current.
Open circuit.
Open circuit.
It's a industrial. A voltage source providing zero voltage,
Short.
short circuit again. A current source providing zero current, open circuit. So now these transforms are the familiar one.
Yes.
That's what we were claiming. If you replace S with the j omega, the story was
Same.
okay. That was the difference in Laplace and that frequency domain. In those frequency domain, frequency domain was not providing us the complete solution. It was not discussing the initial values, etc. Okay, but in the Laplace, we have initial conditions, and that's why Laplace is claiming that I have the capability or I could provide the complete solution, not only the steady state but also the transient, not only the natural response but also the forced response. Okay, so let's start the examples and see the application of Laplace in the electric circuit. Questions? Yes? Ibrahim? I don't know why you guys have smile on your faces, yeah. Huh? Being the last lecture, you should be sad.
Yes, sir.
Yes.
Oh my God. We will not have circuit theory anymore. How will we live? I will die. Then I will not solve the circuit.
There is a pigeon in the
Oh
cab.
God. God, please save me. Okay. The thing is, examples 16.1, 16.2 and 16.3, they are very important, but as they have solved them, so I will not solve instead of, despite of example 16.2. Okay? Please go through the examples 16.1. I am going to solve practice problem 16.1. Okay, so okay, practice problem 16.1. They said determine B naught T. Okay, let me draw first. 0.25 farad. 1/4 farad. Connected in parallel with the current source having magnitude 10 euro, which claims that this current source was zero before the time t equal to 0. Unit step function 0, 10. Okay. Inductor of 1 Henry. And then T. Okay. He's asking you to find out the voltage across this 4 ohm resistor. And the next thing he said, assuming zero initial conditions. Okay, initial conditions are zero. So, forget about the Laplace. If you are free to choose any of the method, then do. This current source, this is not the sinusoidal one. So no, you are not going to consider the phasors. Okay, phasor was the translation of sinusoids. Okay, This time, unfortunately, if you have the contents of this course only, then you have to jump into the Laplace to solve them. Otherwise, you have to consider the time domain scenario as well. You have to make equation, you have to apply voltage, KVL here.
Yes, sir.
This will give you differential equation. KCL, this will give you integral equation. Okay, so that will be a complicated mathematics will be involved there. Okay. Okay, so Laplace. Let's conclude that we are going to solve this circuit by using Laplace. Okay, Ibrahim?
Yes, sir.
So far so good? You sure? Okay. So we just see that if we have a capacitor in the time domain, transformation of the capacitor is either either we have to plug in a current source or the voltage source. Current source or the voltage source. Okay, whatsoever the directions are. Blessing in disguise, thanks to him, he said that please consider the initial conditions, initial values, assuming zero initial conditions. Zero initial conditions means the value of current at time t is equal to 0 is 0. The value of voltage at time t is equal to 0. If we implement it here, okay, so let's transform the circuit. 1 over SC, 0.25 times S, Janab, Amran. What is the Laplace transform of this source? Current source. 10 u of t. 10 by S. Very good. The Laplace of unit step function u of t is 1 over S. Okay? Good. Amran. SC? Oh, sorry, SL? And the value of L is 1. So it's resistor is so when we will solve this circuit, we will be able to find out the V naught S, not the V naught T. But in the question, he is asking to find out the value of V naught T. It means we have to replace inverse Laplace. Okay? And please consider it. If you left the answer in the Laplace domain, you will not be able to secure full marks. Okay? We have iterated it number of times. We have repeated it number of times. Okay? That we need answer in the same domain in which the question is. Okay? It's your headache, it's your issue that you are transforming the circuit, time domain circuit, in the Laplace or in the frequency domain or whatsoever you are doing, howsoever you are handling that. Even if he has given you the quantities in the root mean squares. Okay? Remember that?
Yes.
Then we need the answer in the RMS values. Okay? It's not up to you that you are free to use the maximum magnitude or whatsoever. Okay? It's clear?
Yes.
Okay. So let's try to find out the voltage across the 4 ohm resistor. Yes. Remember all the techniques, formulas that we had learned so far, either in the ECA 1 or ECA 2, are true. What's your choice? Okay. Voltage divider. Inductor and resistor are in series. So that is the first condition of voltage divider. Okay, that's good. Ikra, there was a second condition to apply the voltage divider as well. What was that?
सर दो कंपोनेंट सीरीज में उसकी वोल्टेज भी होना चाहिए
उनके across. Voltage across these components should be provided. So, do you have that voltage? Okay, that's a good way as well. That as we have this impedance in parallel with this current source, so we could use source transformation and transform this current source in voltage source in series with this capacitor. Okay, then all of this will be in series and you will go. Okay, any other thing? Abdullah. Oh, sorry. Source transformation. Any other? No, that option is gone. We have many methods here: KVL, KCL, Thevenin, Norton, voltage divider, current divider, and any other thing.
But not apply there, sir.
Well, try to apply. Think on it. He has already utilized the voltage divider and source transformation. Kamran.
Sir, मैश भी लग सकता है.
Okay.
दो
This is the mesh 1 and this is the mesh 2. You could apply mesh analysis as well. I do agree.
I think KCL.
Okay, it's totally up to you. KCL. KCL node.
This node.
This node.
Yes.
This node.
This one.
Okay. Come on.
KCL भी लग सकता है.
Come up with the relatively nice idea. Ibrahim. Nodal analysis. Okay. Node voltage. This node voltage. So we will find out the voltage on this node and voltage. Okay, we will find out the voltage on this node. This is V naught as well. Okay. Any other thing? Voltage divider. KVL. KVL. Voltage across this plus voltage across this plus voltage across this. So mesh analysis, super mesh. Okay. चिड़िया तोड़ना ना मारो यार.
The source of transformation
That's gone. That method is gone.
वो easy है.
No, you have one more very easy method. Voltage divider.
Current.
Please. Yeah. If you have a current source in parallel with components.
Then we must apply.
No, it's not about a must. You could prefer that. Okay. Current flowing in this. Current flowing in this. Okay. This is a parallel. So if you got the current flowing in this series components, you got the current flowing in this, and V is equal to IS or IC. Okay. So it's totally up to you. I'm not saying that you should apply the current divider here. Okay. But for me, when you apply voltage divider, then you have to apply another technique as well, source transformation. Okay. When you are applying KVL or mesh analysis, then you have to apply super mesh. Okay. Yeah, that is a good idea to apply nodal analysis. Okay. And find out the node. but then too you have to find out two equations. One equation for this node and one equation for that node. Okay? But for the current divider, you will have only one equation. Okay? You have the calculator, you can find out the rest of the things. So let me solve that for you. Okay, the current is equal to 4 by s. 4 by s plus 4 plus s. Okay, when you solve that, you will find out 40 divided by s. Repeated loop or repeated pole.
Yes, sir.
Okay? Okay. So, as you have to provide the solution in the time domain, okay, so you have to make. Yeah. What's the question? की है? हैं? ऐसे तुम जाके करोगे तो फिर पता चलेगा की है? हैं? A? That's ampere. You know what right? Come on, please. It's not A for Aftab, man. Okay. Rest of the thing is okay. Okay. When you will solve this by applying current divider or by applying nodal analysis or by using voltage divider, whatsoever the method that you have suggested, inshallah you will come up with this current, and the voltage will be 4 times I2, that is 160 divided by S. Okay, this will be the voltage source. This will be the voltage across this in the Laplace domain. In the Laplace domain. We need the answer in the time domain, so we have to find out a suitable expression so that we can take help from the table 16.1 and transform the Laplace, apply the Laplace, inverse Laplace. So, either by comparing the coefficients, either by applying the residue method, A over S, B over plus
C over S.
very good. So you will multiply S in order to find out the A. You have to multiply S with this expression. S will be cancelled out by S.
Yes, sir.
S is equal to 0 as well. So 2 square 4, 160 divided by 4. A will be
40.
A is 40 plus. When you will multiply this expression with S plus 2 square and put S is equal to minus 2, then you will find out minus 80 divided by S plus 2. And thirdly, when you will multiply V naught S with S plus 2 square and take derivative of that with respect to S, you will find out minus 40. Okay? We have already practiced it in the last lectures. Okay? So, okay. So these are relatively familiar terms. We know the T is equal to 40 U of T minus 80 T exponential. Ibrahim, solve it for us. You have this expression in the Laplace domain. Now apply inverse Laplace and find out the answer in the time domain. You have table 16.2. No, it's sorry, table 15 point. Why? 1 over S is the inverse of. Very good. Next.
minus 80 t e s power minus ut.
Why?
1 over s plus 2 whole square inverse t into e raised to minus 80.
T exponential of minus. What is the value of a here? Very good. U of t. Okay. G next.
Minus 40 e raised to power minus 2t.
You sure?
Yes, sir. 1 over s plus 2.
Okay, it's only exponential of minus.
Yes.
But when you have the repeated poles,
Yes.
you had t exponential. Okay. What is the unit of this equation, Moniza? What are the units? Huh? Unit. What is the unit of this equation? Volt. It's not V for victory, yeah? You could say the where from we got that V. Okay. So this is your answer in the time domain. This is the voltage across. Okay.
Yes, sir.
Okay. As we don't have any initial conditions, so that's a steady state. So before going to start practice problem 16.2, let's consider example 16.2. Open your books. Example 16.2. Open your books. Okay. Okay, let's have a break of 5 minutes.
Yes, sir.
Yes.
Example 16.2. It said that find V naught T. Let me draw. Two times delta of T on page. V naught of T. Okay. It's saying that find V naught T in the circuit of figure 16.7. Assume V naught of 0. Voltage V naught of T. Voltage across this capacitor at time T is equal to 0. Initial value. Okay. Is not equal to 0 this time. Last example mein it was 0. Okay. So that's why 5 volts. This is a hint that this time when we will transform our capacitor into the Laplace domain, it will not only be the single capacitor. We will have to plug in a current and voltage source, whatsoever the configuration. Okay. So let's transform the circuit. Voltage source. G. Man.
Yes.
What is the transformation of this? Expansion of minus t. Why not you are consulting the table? What the option?
S plus 1.
1 over S
Yes.
plus A.
10 over s plus a.
Yes.
Okay. 10 ohm will remain 10 ohm. 10 ohm will remain 10 ohm. This capacitor will be 1 over SC. 0.1s, and we could plug we could plug current source in parallel.
Yes.
Okay. Why would we plug voltage source in series? Okay. The possible answer could be it will give us ease
Yes,
to
sir.
apply a simple method.
Yes, sir.
For example, if I apply current source here, Please correct me if the symbol is not good. It's upward, right?
Yes.
Okay. And the magnitude of this is
C.
S and value no C.
Yes, sir.
C and magnitude of take it. So 5C and C is 0.1, so it's 0.5.
Yes, sir.
Okay. This is again a current source. 2 times delta of T, 1, 2 amperes. Now I have to find out the voltage across. Only now this V of T is transformed to units. He has utilized nodal analysis. Okay. I would like to prefer current divider. Okay. That's come the reason why we have used the current source in parallel. Current source. Very good. If you use source transformation, then there is a current source. Okay. Now I can combine this. It will not be the value. The new value will be 1 over s plus 1. Okay. This will be the new value. So now I can combine these 3 current sources into one single current source. Okay. The value 2s plus. Okay. Similarly, I can combine these 2 resistors. 10, 10, 100, 100 divided by 20, 5. Okay?
Yes, sir.
All set to apply the current. Okay? So, in this way, current divider 5 divided by 5 plus 1 over 5 minus multiply by this term. When we solve this, we will find out the answer. Okay, rest of the things are same. Then he will apply. Then we will have to apply inverse Laplace. Okay. I just want to show you that instead of applying the suggested method, the nodal analysis, he has applied nodal analysis. So we can also use other method. Okay. Okay. Let's try practice problem 16.2. That was example 16.2 that is solved by the authors. Okay, Janab. In practice problem 16.2, 75 exponential of minus 2t 1 ohm 2 Henry 2 ohm. Okay. Find out V naught of t in the circuit shown in figure 16.9. Note that since the voltage input is multiplied by U of t, the voltage source is a short for all t less than 0 and current flowing in the inductor before the experiment or before the time t is equal to 0 or time less than 0, current is not, initial condition is 0. So unlike the example, or just like the practice problem 16.1, we will have to plug in SC there. Sorry, SL. Okay, and that's our transformation in. It will be t exponential. What will be the 75 exponential of minus 2t? Ibrahim, 75 exponential of minus 2t u of t.
1 over
75 over
1 over 2 plus
s plus
2.
2. Okay. So now this circuit is in Laplace domain. Okay. When we solve this,
AUT 1 over S नहीं है ना?
yeah. नहीं उसके साथ ऐसे रीड ऑन द टेबल अगेन उसने बताया कि नीचे u of t सबके साथ ऊपर मल्टीप्लाई करें. Okay, very good. So we could easily apply voltage divider. Okay, voltage across this resistor is same the voltage across this inductor. Okay, so we can combine this and make a single impedance. Okay, then apply the voltage divider. S plus 1. When we combine these two impedances, this will be 2s over s plus 1 and whole multiplied by 75 by s plus 2. It will give me 150s over s plus 2, 3s plus 1. Okay. And then we'll solve this one by having residue or I have 60 over s plus 2 minus 30 over 3s plus 1, and in the time domain it is volt. Okay? Remaining mathematical steps are totally up to you. Okay. Let's come to the point. Practice problem 16.3. Okay, Janab. The benefit of Laplace in the circuit. Okay? I need your full attention now. That was just warm up.
Yes, sir.
We were just trying to familiarize you guys with the Laplace. Now let's see the magic of Laplace. Okay? Abdullah?
Yes, sir.
Are you ready?
Yes, sir.
Okay. You may go.
Thank you, sir.
Yeah, we are ready to go. You may go. Nikal. Okay, Janab. Practice problem 16.3. The switch in figure. Oh my god, he introduced the switches just like he did in the chapter number 8 and chapter number 7.
Yes, I remember.
Ah, thank you. Initially, there was a current source at terminal A and there was a voltage source at terminal B. I not show any of this. We not show. And there are RC circuit. There is a RC circuit. Okay, and this circuit is connected to these sources one by one. It said that has been in position B for a long time. It means that before the time 0, before the time 0, this RC was connected the B. Okay, for a long time. He used the word for a long time. Means, do you remember that tau? RC, tau is equal to RC. That was, what was at that time? Saturation time or transition time? What was the term? It was the time required to charge or discharge the capacitor. Time constant. Yes, the term was time constant. Okay. So it was connected at the node B. So that voltage source got the enough chance, or this capacitor got the enough time to charge. Okay. It is moved to position A at time t is equal to 0. Okay, before the time t is equal to 0, it was connected at B. At time t is equal to 0, it's disconnect from. Okay, or let me draw this in the dash lines, and that is all. Dash lines, and this is solid line. Okay. Determine V of t for t greater than 0. V of t is the voltage across the capacitor. T greater than 0. T greater than 0 means when the switch is, or the RC circuit is connected with the current source. Okay? Do you understand the question?
Yes.
Huh? Abdullah, you sure? So this time when we use to transform this circuit in the Laplace, should we consider the initial states or not? The first thing that you have to encounter. अब जो हम इस कैपेसिटर को ट्रांसफॉर्म करेंगे, so we have to plug a single capacitor with the impedance 1 over SC, or we have to plug another current or voltage source as well. That's the first question. The answer was in the statement. If you say, I can repeat it for you guys. Okay. Okay. Listen to the question carefully. The switch in figure 16.11 has been in position B for a long time. Note the word long time. Long time means, Abdullah, the switch was connected, so the circuit was, this was the circuit for the long time. Before our experiment, suppose there was some other group who was conducting the experiment. Okay, they used the same RC, resistor and capacitor in parallel, and provided voltage source to this circuit. Okay, right after them, we start our experiment, and instead of that voltage source, we plug
Out.
a current source. Okay. Now we are interested that what will be the voltage across this capacitor in our experiment. Okay. So what about the voltage that was stored by the other group across this capacitor. Is it in vain? We shouldn't care about that, or we should consider that voltage in our experiment as well. We have to consider, because our balance is starting from 0 plus.
Yes, sir.
Okay, please.
सर वोल्टेज जो लगा वो दोनों जो कंपोनेंट बीच लगे ठीक दोनों के पैरेलल में है जो वोल्टेज इनपुट में होगा वही आउटपुट में जाएगा
Yes, but that was the story before the time t is equal to 0.
Yes, sir.
Or that was the story for the students who has conducted the experiment before us. Okay, they have stored an amount of voltage across this capacitor. Okay, now we are going to start the experiment. And we are interested by applying a current source here. Okay, instead of this voltage source, that how much that capacitor will charge, how much voltage will be across that capacitor. Okay, so in all this procedure, should we consider the previous or not?
Yes, consider.
Abdullah?
Yes.
There are two cases. Either we should give that capacitor enough time to discharge. Okay? And there will be no voltage across that capacitor. All the voltage that the other group have stored before our experiment, before time t is equal to 0, is gone then. And the voltage across capacitor is equal to 0 voltage. We have brand new capacitor again. Okay?
Yes, sir.
But nature of the question is not like that. He is saying has been in position B for a long time, minus infinity to time t is equal to 0, and that was the enough time for the tau, for the time constant, to charge the capacitor, to store the voltage. Okay, so I don't want to give you the clear hint. I don't want to use the word initial condition. Now initial condition is not equal to 0. He has not stated that word directly, but indirectly with the word long time. Ikra, do you want break? Okay, then consider it. With the word long time, he stated that initial value is not equal to 0. Initial value means V at 0 is not equal to 0.
Yes,
Yes, sir.
At time t is equal to 0, when this switch is cut off from here and connect to this current source, when our experiment gets started, there is some voltage across this capacitor and we have to consider that. Okay? So in other words, he has given us a hint that when we have to transform this capacitor in the Laplace, we have to consider the other component, the source of the current, voltage source or the current source, whatsoever. Okay? Got it? So you have to read below. I have spent more than 5 minutes on this thing. I think around 10 minutes to describe the question. And just give you hint that you have to read between the lines very carefully. Okay? You have to read the question. You have to read between the lines. Yes? You're getting me? You sure? Huh? Okay. So there was a hint that how we have to transform the circuit. So let's transform. Current source, I know as resistor, capacitor, and 1 over SC, and now again we have the option. We could plug a voltage source in series and a current source in parallel. depending upon the nature or depending upon the structure of the circuit, if we apply current source here, okay, then we could easily apply the current divider or the node analysis. Okay. On the other hand, if we apply voltage source here, we could again solve that circuit. It's not that we will not be able to solve that, but this time we might have to apply mesh analysis. Okay, so you can apply whatsoever the configuration you want. Let me try the current source. Okay, the current source of magnitude C, capacitance of this capacitor which is not given, and V naught, the value of the voltage across the capacitor at time t is equal to 0, which is again not given, so we have used that. Okay, in the examples in the practice problem 16.1 he has given that values. Okay, so we plug in, but this time he has not given that values. Okay, so now onwards, the guy who will not concentrate on the lecture, okay, he will be penalized to provide breakfast for everyone. Okay? Okay? Yeah. Oh, yeah, that's good. Okay. Okay, so Abdullah will provide breakfast for everyone after the class.
Yes, sir.
Okay? It doesn't mean that no, you guys are free of it. You can join them. Okay? So, okay? So Abdullah is the first one who will give us the treat. So let's see who is going to join him. Okay, Abdullah?
सर मैं आपको खिलाना चाहता
No. It's about the class.
हूँ मैं रोज खिलाता
Okay, come on. Okay, let's start with the current divider. And let me go very fast. Okay, so when we will apply current divider across this capacitor and have some mathematical steps, 3 or 4 steps. Okay, then you will find out this expression. But we were interested in voltage across this. That was the current flowing through the capacitor. Current flowing through the capacitor, but we are interested in voltage across the capacitor. So V is equal to IZ, and Z is 1 over SC. Okay, so I naught R plus S R C V naught S into R plus. That's the voltage across the capacitor. But in Laplace transformation, we are interested, or we have been asked to find out the voltage across the capacitor in the time domain. Okay, so let's take the inverse Laplace. V of S is equal to A over S 1 plus S times RC. Okay. So. Oh. A is I naught R, the value of A, and the value of B is V naught minus R multiplied by RC. So my values for the function is no. Let me raise. Okay. I naught R over S. Shall You want to join, Abdullah?
ये वहाँ जाके निकल जाता है पैसे भी ना देने पड़ते
Abdullah.
अभी कल ना तुमने रोटी खाई
Okay, okay. Okay, come back. So that's the expression which is ready to be inverse. Okay, 1 over s and s plus a. Okay, 1 over r. So if I use to transform that, yes, v of t is equal to I naught r. Yes, 1 over s is equal to okay plus yes exponential of minus t multiplied by a. A is 1 over rc multiplied by r denominator as it is, and that's connect with the u of t, and that's your voltage. Okay, it's not about the answer, it's about the analysis. That's your answer that is required. But if you analyze this, and we could also find out the initial and final conditions here as well. Okay, wait for that. If you analyze this, it will give you information about the steady and transition period. Steady state and the transition period. Cubic? Can you see? Then see. Time, voltage, okay, and there was a plot like that was your steady, and that was the transition. Okay, or it could be vice versa as well. Again, this is steady, this is transition period. Okay, so this component giving us steady state condition, and this is the transition phase. Okay, which majorly depend upon that was your time constant for the RC circuit, tau, T by tau. Okay, so if you put values here, let's fix I naught R, V naught, I naught R, and C, then this plot will be like this. Okay, this is the transition period, that when time t is equal to 1, 2, 3, the voltage was varying, but at this time it's static. Yes, and u of t means before the time t is equal to 0. Ibrahim? Okay, let's try to find out the initial and the final values. Remember, how do we find that? V of 0 and V of infinity in the Laplace by using Laplace. S multiplied by V of S, limit S tends to infinity. And V of infinity is equal to S V of S, limit S tends to 0 for the final value and for the limit. Okay, so here you can find out those values. In the next example, he has asked. In this example, he didn't ask to find out the initial or final, but in order to justify that it is the steady and it is the transition phase, you can find out the initial and final values. Okay.
Yes.
So S tends to infinity. S से multiply. If you multiply S This S will be cancelled out by this S and take S common. 1 plus 1 over RSC. This S will be cancelled out by this. Put S tends to infinity. 1 over infinity 0. This I naught R minus I naught R. किसने कहा? Yeah, he said. को समझ आई क्या हुआ?
हाँ जी आ रही सर।
I naught R. This term 1 over infinity. S tends to infinity है ना?
Yes sir.
1 over infinity 0. 1 divided आ गया बस. V naught minus I naught.
Yes sir.
I naught R cancelled out by.
I know that.
So the thing that Avyas has pointed out, that initially whatsoever the voltage provided by this voltage source was stored because they are in parallel, and that's its initial condition at time t is equal to 0. All the voltage that was provided was across the capacitor. Okay?
Yes.
Similarly, you can find out the infinite value. What will the value at infinity? That is again S. Limit S tends to 0. Okay? When we multiply S with the S will be cancelled out. 1 over infinity or again? 1 over 0 infinity. Infinity. 1 over infinity 0. So I naught R is the steady state when we will be at the time infinity. Okay? That's what we used to say, that it is the steady state. I naught R. क्लास में आई कि नहीं? Okay? And what happened? Meanwhile, this term will give you the information. Okay? In between 0, time t is equal to 0 to infinite, transition state will give you. So, in this way, we can find out the steady state and transition response. There was another term, natural and forced response. What was the natural response and what was the forced response? You can also find out from there, from the same expression. This is the core of this topic. Okay? You have to find out these things. You have to find out the initial final values. You have to find out steady state, transition, a complete response. Okay? So please concentrate here. So where did I this if I use transform it, rearrange it. You can cover this side.
Yes sir.
That's the drawback of recording the lecture. Everyone is relaxed. Okay, we will go.
सोया हुआ।
Alright.
तू बातों पे लगाया है तूने।
It is a natural response of the circuit. Okay? It is the force. If you rearrange the equation, V naught exponential of minus, that is similar to the response that you have obtained in the chapter number 8 when we were dealing the complete response. You were finding out the natural response separately when the switch was there, okay, and then you were finding out the force response when the switch was toggled to some other position. Okay, so these were kind of results that you were finding out. But you could compare. I'm requesting you, please compare these questions that you have solved with the Laplace and that you had solved without the Laplace in the time domain. That how much the mathematical redundancy is reduced. Okay. Okay. So before going to start other example, why don't you separate the
सर काफी
okay, you can solve the practice problem 16.6 on your own. We have covered everything here. No?
Yes, sir. Yes, sir.
I just want to show that he was asking to solve that circuit by using Thevenin. For example, he want to emphasize on the technique Thevenin theorem. That's why he has put the condition that you are supposed to solve these problems with the Thevenin theorem. Okay. For example, if he has not put that condition and you are free to solve, then you can solve the same problem without using the Thevenin theorem. I just want to emphasize and want to provide you the solution without applying the Thevenin theorem, but it's okay. I could see that that's enough.
yes
So,
sir.
so that's okay. Please try to solve by using the Thevenin and Norton theorem.
Yes, sir.
Okay.
Yes, sir.
So hint about the exams, because this is the last session between them. There are maximum chances that we combine Thevenin and Laplace. Okay. And the core is that whole Laplace, the target of the Laplace, the reason why we were using Laplace was we need complete solution. Okay, in one step. And that was the claim of Laplace, where we started. Okay, Laplace said that okay, Laplace can provide you the solution or analysis of AC circuits while you have any kind of AC signal. Claim number 1. And the claim number 2 of Laplace was, I will provide you the complete solution in one step. Complete solution means containing steady and transient response or containing natural force response, instead of solve the circuit separately and then combine them. Okay, so we will evaluate these claims by applying some relatively different kind of technique of Thevenin. Okay, so I hope that by practice you will be able to find out the complete response of a circuit which is operated on as any AC signal. Okay, by applying any technique like Thevenin, Norton, current divider, mesh analysis, etc. Okay, so that's all from the today's session. Let's conclude the subject. Okay, so the aim of the subject was to give you glimpse, to give you some insight that how you can analyze an electric circuit containing a resistor, capacitor, inductor, and AC sources. Okay, we started the discussion with the simplest most and the most valuable source, AC source, that was sinusoid. Okay, we transform that sinusoid in the phasor form and see that by using the phasor form, our mathematical life becomes easy when V is equal to IZ for everyone. Before that, V is equal to IR for resistor only. In the time domain, the current and voltage relation for the resistor was relatively easy. V is equal to IR. But the current and voltage relation for the capacitor and inductor, they involve differential and integral equations. Okay. So then we see that our integral equations or differential equations transform in the algebraic equations. We solve them. Then when we move forward, we see that there are number of terminologies regarding the power. When a circuit is operated on the AC signals, there are number of terminologies and a very helpful, a very valuable theorem, maximum power transfer theorem. which states that when impedance will be complex conjugate, receptor and sender's impedance, source and load's impedance will be complex conjugate, then you will be able to transform maximum power from the source to the receiver, to the load. Then there was some magics of frequency, that if we just tune the frequency, we can find out the magnitude of our required frequency range, which was called filters, frequency response. Okay, and finally you see that if instead of all of these stories were true for the phasors, for the sinusoid signals, right? If instead of sinusoid signals we have other AC signals, then how could we analyze our circuit? Circuit analysis, the subject is circuit analysis of AC signals. We apply Laplace, which has the claim that Laplace could provide you the solution of any nature of AC signal, and it will give you the complete solution in one step. Okay. Meanwhile, we find out Laplace transform, inverse Laplace transform, properties of Laplace transform, and finally we apply all of this Laplace content to the electric circuit today. Okay, and see that claims of Laplace are true, like this or like this. Okay, that was all about this subject. If you have any question, you are more than welcome to ask. Otherwise, thank you very much.